Yeah, so number one should be speed is decreasing because velocity and acceleration have opposite signs. Number two, the answer is supposed to be 4.
Why is it from the right?
Good question. You guys have a question about that? So this is one of those trickier limits for sure. Before I address that, are you guys okay with number 1? Any questions on 1? I'd like to kind of go in order. We're all okay with 1? Okay then, so number 2, let me see here. I'll do this, I guess. Okay, so when you're doing the limit of a composite function like this, what you want to do is you want to consider the limit of the input function first. So if I say, all right, limit as x approaches 1 of f of x, that's clearly 3, right? So then what you would do is you'd say, all right, well then let's take that, and let's make that the limit as x approaches 3 of g of x. And this is where we run into an issue, right? Because we look at it and say, well, as x approaches 3 on g of x, we have a point of discontinuity, so from the right, from the left, or neither would matter, right? It would make a difference. So how do we know that it's from the right? I go back to the graph of f of x, and we got to look at this 3 over here, and we got to decide, are the y values of f of x approaching 3 from numbers that are bigger than 3 or less than 3? So I'll use the graph to help me. So like right here, this y value, 3.5. This y value here, 3.2, 3.1, obviously heading towards 3. From this side, it's the exact same thing, 3.5, 3.2, 3.1. So no matter which way I approach 1, I'm approaching 3 from numbers that are bigger than 3. Right? That makes sense? So if I'm approaching a y value of 3 from numbers that are bigger than 3, that means I'm approaching from the right of 3 when I apply that limit to the outside function. Let me redraw the graph so that it would be ultimately, so this is from the right. If I redrew the graph like this, can you all see how that would end up being 3 from the left? I'd be approaching 3 from numbers that are smaller than 3. So then it would be, in that case, the answer would turn into what, 2? Because I'd be approaching from the left on the other graph. Tricky, probably the trickiest limits possible, in my opinion. What do y'all think? I feel like somewhere in there you got it. Yeah, okay. Luke, you had your hand up too. Are you okay with that?
Yeah.
Okay. These explanations always sound so good up here. I know sometimes the translation gets lost, so let me know if I can help more or differently, anything like that. Any other thoughts on 2? Thanks for asking, Luke. All right, so then number 3 is right here. I got 1.403 for a final answer. You guys get the same thing? Okay, good. So I found my intersection points, 0, 1, and whatever that other one is. There we go. And set up my integral with the parabola minus the exponential, and then definitely use Math 9 to finish that one out. So a chance to reflect and think. Do you have any other thoughts or questions? Okay, cool. So here's what we're going to do today. Not that. We're going to do this. There we go. Okay, so this first question is going to be a nice segue from what we just did. And it might push you a little bit. It does say calculator active, and so I would strongly encourage you to take that to heart. I would graph these. Before I do anything else, I would graph these trying to figure out what's going on. While you're doing that, I am going to hand back your quizzes from yesterday. And remember, this is the quiz that you guys have basically a week to get retries done on. Saw a couple of you this morning. Tomorrow morning is wide open for you, so please do come in to get some retries in on this or any of the other Unit 6 quizzes. A lot of good stuff on these. I can tell you guys studied like crazy. Might have been a few little oopses with minus signs and plus signs here and there, or that sort of thing, but I can tell you guys really put in a good effort to prepare. So, yeah, check these out. For the most part, really good. Other than maybe a few little minor, very fixable errors. Neat. There you go. Check. There you go. Gavin, they're out here, right?
Oh.
Cole, there's yours. Let's go. There is one.
Yeah.
Joy, put your quiz from yesterday on your table. Jed, there you go. And Hunter, there you go. Did everybody get a quiz back that was expecting one? I'm gonna have you guys finish this one, but I thought I would help you kind of get started with what's going on here and kind of with the graphing thing. So I'm gonna get my graphing up there. X cubed squared minus x plus 1 and g of x equals 7 sine x plus 1. Okay, so I've got my graph going on up there. Do you have your graph on your screen? Some pretty crazy graphs for sure. So let's talk about what this is. I want to maybe kind of help you guys get this set up and see what you can do to finish it. Would it be fair to say, based on our experiment yesterday and then the one practice we did yesterday, when you're finding the area between two curves, isn't essentially, if you want to boil it down to the simplest possible way of putting it, isn't it integral of high minus low times dx or dy or whatever? Basically the integral is high minus low. You all okay with that? So did you guys notice that there are two different regions here that are enclosed by these graphs? And did you also notice that within those regions, the high and the low flip-flop? Mm-hmm. So what do you think you're going to have to do?
Two different angles.
Two separate integrals. That's right. So hopefully that's enough for you to go off of. It probably is, because you guys are seem like you're really good at this. So see if you can set up two separate integrals whose total would end up being the full total area enclosed or bounded by those graphs, okay? So I'll let you guys work on that idea of two separate integrals, and then we'll get some answers up there in a second. What's up, Mary? Yeah, what's up? Ooh. So let's see here. Do you guys agree on the intersection points?
Yeah.
Completely agree on the intersection points. So let's see here. So for the one on the left, that would be f minus g. Now make sure you have dx's there and there. And then of course the other one would be g minus f. You guys totally agree on those intersection points? So it must be somehow the way you're putting it in the calculator, where you guys disagree.
This integral is 1. You got that.
Which integral is one?
This,
Oh, it's bars.
Just if that is 1.
Yep.
Like that. This number.
None of
Since it
that
can't be
can
above
be
this area, I added it to that.
Yeah. Okay, hold on. Let me just. Okay, so you
So
did.
this is what I got.
So you shouldn't be getting a negative there. That's the There's a, I think it's a parentheses thing, isn't it? Oh, okay. Was it plus one on the other one? No, you got minus one there. Plus one. Yeah, I don't know. Yeah, whatever area you get is one. So now you're getting a bigger number. And Hunter is like 6. Oh. So, how about this? Let me show you a shortcut you can do. So, we'll see if that might be the right answer. So here is your, this is F, this is G. Okay, awesome. Let me show you an easy way to do this. So if I was going to do this, I just want to remember that Y1 is F, Y2 is G. So I'm going to clear all this out. It's okay. I'll go math 9. And you got your numbers in there. I'm just going to go alpha trace Y1 minus alpha trace Y2 dx. And so I know what my Y1 is F, my Y2 is G. So that prevents me from having to like retype it and take forever and probably mess up the X plus 1, right? Whatever it was. Obviously you do want to get your limits in there, but does that help? Okay. Awesome.
No, you were to
Let's see here. So this looks like this is the left area. So, and I think these are the same intersection points as those guys got. So left area would be, yeah, cubic minus trig function, yep, plus the right area goes up there to about of trig minus cubic. Seems reasonable. Yeah. Seems very reasonable.
Yeah, exactly. I said full.
1.402.
middle row. I literally pour everyone's on. I literally like tell you right now. Like, it's literally the issue.
Well, 13 is like one part, and then you get the other part of that. Any thoughts, any questions, guys? Your binding intersection is exactly what you should be doing. What's up? Everybody else? Yeah. Okay, so I think I'm going to do two things here. Merrick, do you think other people know about that alpha trace thing? No. Okay, that would be helpful for everybody to know about, wouldn't it? Yeah. All right, so check this out, please. So essentially what we need to do is we need to find several intersection points. And walking around, I saw that you guys did a nice job with that. I'm going to find my, I'll call this the green area first. So this is going to be integral from, and was it like negative 3.077?
Yeah.
Negative 3.077. That's this x value right here. To, is it positive 0.067? Help me out. I'm just going by memory. Oh, negative. That's right. Yeah. Negative 0.067. Oh, 0.67. There we go. 670. I think I just flipped those numbers around perhaps. Okay. So for my green area, it's going to be F minus G because F is the higher function on that interval. Then I will add to that the integral from negative 0.670. It's like, isn't it like 1.29 something? 1.296? Okay. For that one, it would be g of x minus f of x. So that integrand has had to flip the order there, because now for this other area, which I am labeling with a purple shading, for the purple area, the purple graph is the higher graph, so it needs to be G minus F. So then, obviously, at this point, it's Math 9 time. I say obviously, hoping that it's obvious, right? Please, for goodness sake, use Math 9. And it's, what, 21.402?
Yes.
I think, for a final answer. So maybe a point to take away from this is, let's pretend that number 1 was some quiz question or test question or on the AP test or something along those lines. What I've written up there would suffice for full credit. If the calculator is active, I want to see how you set up your integrals and got all that work set up. You can even use F's and G's in there. And then an answer. That's all we're really looking for. Okay, so I want to talk about that thing I talked about with Merrick. So please check this out. I'm convinced, I think Merrick is also convinced this would be helpful for you all, especially in a question like this. And you might find other questions that come up like this. I want to show you how you can use the TI-84 to your advantage. So in your calculator, did you not put these two functions in there? So, you had y1 as x cubed plus 2x squared minus x. Was it plus 1? I forgot. I can't quite see it on my screen. So plus 1. And then g of x was 7 sine of x plus 1. So you graphed it and you found your intersection points and all that good stuff. But remember that f of x is in your y1 and g of x is in your y2. Here's what I would do if I were you. When it came to evaluating that integral, I would go, just like you, I would go math 9, and I'd get my numbers in there, negative 3 point, whatever it was, 0.7 or something. I'm not too worried about these, and negative 0.67. And then in my integrand, what I'm going to do is this. You just watch the red button pushes. I'm going to go alpha trace. Do you see why this is useful? Alpha trace. I remember that f of x is in y1 and g of x is in y2. All I have to do now is say y1 minus alpha trace y2 dx. There's my integral. Since I put f of x in y1 and g of x in y2, my calculator knows exactly what I'm doing. Why would this be useful? Screwing up your parentheses, right? Or accidentally making a plus a minus or a 2 a 5, or God only knows what we do. We do silly things. This would prevent you from doing that. As long as you input them correctly in the start, if you use them later on, you won't make any mistakes, right? Your calculator doesn't lose minus signs. Yes, I hope that. And then, of course, you'd add the other one onto it. You go plus math 9 with the other one. Only it'd be y2 minus y1, and you'd be in good shape. Hopefully useful. We good? All right. So you guys have any follow-up questions on number 1? Can anybody identify a word on number 1 that's a big hint that you might have to split it up into 2 integrals? Say again? I don't see the word and in number 1. Oh, did I say number 2? I'm going to say number 1. Like in number 1, oh, the word and between the 2. Yeah, I don't think, that doesn't tell me that I got to split it up, because those are just my 2 boundaries. Yes, but there's a word in there that tells me that I might have to think about this whole splitting up into 2. Total. Because think about it, like when you go to the grocery store and they give you a total, aren't they adding up probably like several items? Like usually the word total means they got to add some stuff up. So here, if you see total area, you need to be thinking, oh, I bet you it's one of those ones where the high and the low switch and there's like 2 or 3 little clumps of area that I need to total. So something to think about. All right, so now, if you would, oh, this is such a good one. Again, calculator active. Please look at number 2. This one's piecewise. Obviously, you can see that. So use your calculator to help you with the graph. And see what the graph ends up looking like. And let's find the area enclosed by the x-axis and that graph. looks triangle-ish. Yeah. The two lateral sides obviously have some curve to them, but it looks sort of triangle-y. Triangle-ish. Okay. So let's see here. Graphic-wise, I'll try to get this up on the screen. We can compare, but I'm sure you have it right. Y, X. So the exponential looks like this. And then I think this joining point is right here at 3. That intersection point. Okay, so we're looking for this area right here. It's very lightly shaded in purple. Can any of you guys identify what we ought to do? Anything makes sense logically? Yeah, what do you think?
I split it up into two integrals.
Why on earth would you do that?
Because it's a piecewise function.
Yep, and what's going to happen at the intersection point?
One's gonna exist and one's not.
Sure, yeah, I agree. And so, let me, go ahead.
Confuses the question.
My question was, what's happening at the joining point, right?
Changing.
Yeah, the functions are switching. Let me put it like this. I kind of like this. I like this analogy. Would you guys agree? Oh, shoot, I want actually a different color. How about this? Would you guys agree with me that over here, the red graph is telling the representative rectangles how tall to be? And then right there when you get to 3, what happens?
Purple graph.
Now it's the purple graph that tells the representative rectangles how high to be. So they would look, of course, maybe like this. And so because the height of the rectangles, or I would say the graph that determines the height of the rectangles switches, we need to have a brand new integral to account for that. Okay, so did you guys write down anything as far as those of you that decided I need to split this up? Did you write down some integrals? First one would be integral from where to where? 2 to 3, right? That's going to be that first portion of the area that's red. And what would that look like for the integrand?
X minus 4.
Yeah, it would just be the height of the rectangles, dx. And then I'd go plus the integral from where to where?
3 to 5.
We're accumulating now from 3 to 5. Yep. And what about the integrand there?
X minus 5 squared.
There we go. This is the height times the base. It's perfectly set up now. Nice job. And then because the calculator is active, what do we do?
9.
Math 9 time. Did anybody take it all the way through to Math 9?
4.437.
So Hunter thinks it's 4.437. Anybody, you guys agree? Okay, I'm seeing quite a few heads saying yes. Okay. So we're just trying to take a look at area in lots of different varieties of ways. We got one more, but before we do that, are you okay with number 2? Do you have any questions? All right. So let's take a look then at 3. I think 3 is the last one. This might be where there's a little bit of a disconnect between what you did in pre-calc and what we're doing here. And you can just be honest, I'm pretty sure, like DC pre-calc folks, did you guys graph things like this, like sideways parabolas and stuff like that? I don't know why it's not switching. My screen has switched, but oh, there we go. Did you guys do sideways parabolas in DC pre-calc?
I feel like we did.
In regular pre-calc, did you ever do like a sideways parabola? Okay. So we'll take a minute. We'll take a minute to talk about the graph here. So let's fill in some blanks. So everything we've done so far has used vertical representative rectangles like the ones I just drew in there. In certain cases, like the one we're about to look at, a horizontal representative rectangle is better. So instead of the representative rectangle being dx wide, it would be,
DYX.
no, just dy. Just dy wide. And we'll look at why that is if you want here in a second. Because the differential would be dy in this situation, every single variable and every single number within the integral would have to be in terms of y's. Yes, everything is going to have to be y's. So based on your feedback just a second ago about how many of you have seen these graphs, or maybe how many of you remember these graphs, let's take some time together and graph this. So there's my y. There is my x. And the first one, x equals 3 minus y squared. So, of course, if this was y equals 3 minus x squared, you would probably have no issues with this, would you? But it's x equals 3 minus y squared. So can you see how it's parabolic, right? Still parabolic, but because x is in terms of y instead of y being in terms of x, it's this sideways parabola. What do you think the minus on the y squared does to it? And makes the parabola open which direction? Left. That's correct. What about the 3? Which way do you think that's going to move it? It's going to make it move right. Yeah. So this would be, here goes my first attempt at drawing this parabola. That half looks pretty good. Oh man, what happened? There we go. We'll call that good. So this is 3. Make sense? What do you think the other graph is a graph of? It's just a line. In fact, this one would be pretty easy to just get it over into slope-intercept form. It's y equals x minus 1, right? So this graph would look, I don't know, about like that. Okay, so kind of first step here is, can you visualize the region we're finding the area of? Hey, Merrick, please stop. Me too. Okay, so there's my region I'm trying to find the area of. Can I point out why the horizontal representative rectangles are better? I'm going to try to do this by showing you vertical representative rectangles first. So if I did verticals, so if I did dx's, wouldn't the dx rectangles look like this? And so far so good. Like right here, wouldn't it just be integral of green minus red? Integral of green minus red would get me up to about where I am, up to this dotted line. What's going to happen at that dotted line? So let me put it like this. On the region that I've put rectangles in so far, aren't the rectangles told how tall to be by essentially green minus red? Like the top is controlled by green, the bottom is controlled by red. Okay? If I keep moving to the right, what's going to happen? It's just red and red, isn't it? So like these rectangles would look like this. So this would require me to do a separate integral and a weird one, right? Because it would be like red minus red, and there'd be some pluses and minuses involved there. And you actually could do it. You really could. But it would involve 2 integrals, one of which is weird. And so if we could avoid weird things and 2 integrals and just do it with 1 integral, maybe that's better, right? So here's what I would do if I was going to do this in terms of y. Here's what these would look like. These representative rectangles would look like this. Can you see how for every single representative rectangle, the left edge is determined by the green graph and the right edge is determined by the red graph? So because of that consistency, couldn't I just do one integral here? No need to switch. That would be my argument as to why this would be the better method in this case. Okay. So let's set this up. It'd be the integral from somewhere to somewhere. Let's not worry about the somewhere to somewhere yet. Let's just worry about the integrand. What do you guys think is it's going to be high minus low? But this is weird because the high and the low are like, now it's like right and left kind of. What do you think would be the higher function? The higher function here would actually be the red. Because higher, when we talk about something being left and right, isn't higher the right one? And so when we're dealing with dy rectangles, the higher one is actually going to be the one on the right. So I would say this would be 3 minus y squared minus y plus 1 dy. And then what about those limits of integration? Any ideas on how we could find those? Intersection points, yep. So let's do it. I'm just going to say 3 minus y squared equals y plus 1. So it would be 0 equals y squared plus y minus 2. And how do we solve something like that? Quadratic formula or factoring. I bet you we could do factoring faster because I can see that it factors. So it'd be 0 equals y plus 2 times y minus 1, y equals negative 2, y equals 1. And remember what I said at the start there, if you're using dy rectangles, like these horizontal rectangles, then everything has to be y's, including the limits of integration, and they are right there. So I would say the integral from negative 2 to 1 of 3 minus y squared minus, parentheses, y plus 1 dy would get us there. Okay, so a different way of thinking about it, it's the same concept exactly, but the y's are different for sure. Any thoughts, questions? Okay, so I wanted to finish with this one, and I wanted to point out some potential instructions. Yeah, class is almost over, like 2 minutes left. So here, of course, I put find the area. You can see it right there, of course, find the area. So if we followed these instructions exactly, we would find an antiderivative. We'd plug in the 1 and the negative 2 and subtract, right? Every now and then you will see instructions like this, and we didn't have any in here, so I thought I'd show you this. Sometimes it'll say set up, but do not evaluate. So set up but do not evaluate, like an expression for this area. So in a case like that, all you would do is this, and you would stop there. Okay, so I bring this up only because I've seen so many people with the instructions being set up but do not evaluate, just out of habit, they just continue on and they evaluate it, and they spend like 4, 5, 6 minutes evaluating something that they didn't even need to do, wasting time, precious brain power, right, when you could have just moved on. So anyways, thought I'd throw that out there to you, just in case. Y'all good? All right, well, hope you guys have a great weekend. Hopefully I'll see some of you tomorrow morning. Remember, test next Wednesday. So hopefully tomorrow, Monday, Tuesday will be some good opportunities for you to try. Have a great rest of your day.